In this video, we're once again looking at Newton's method. We want to use x0 equals 1, or again x1 equals 1, to approximate the solution to the cube root of x, equaling to 0. Now, I'm doing this example for two reasons. Number one, this is a very clear equation that we can solve. Again, we can cube both sides and get x equals 0 very easily. So it's not really to identify that this particular root is hard to find. What I'm really showing is that, again, this is another way that Newton's method could be asked. Not that I want you to find a root to a function, but I want you to find the solution to an equation that's equal to 0. So if at any point in time I want you to approximate the solution, and I ask you to use Newton's method, you have to get the equation equal to 0. And then your equation equaling to 0 will represent your function that you're trying to approximate. So this is my f of x because it's equal to 0. Now the next detail that I want to also identify with this is that if we actually go through and do all of the math that we're supposed to on this, you'll have to find f prime of x, where this is actually x to the 1/3 power, and therefore my f prime is going to be 1/3 x to the negative 2/3, which is the same thing as 1 divided by 3x to the 2/3. And again, we just don't like negative exponents, so that's why we transition that. Now, my formula for this over here is x1 is equal to, and I'm going to go ahead and use this x0 spot, x0 minus f of x0 divided by f prime of x0. Now, in doing so, all I'm really going to do is I'm going to go ahead and plug in 1 to this function here and this function here and plug it into here. So that's going to give me x1 is equal to 1 minus f of x0 is 1 divided by f prime of x0 would actually be me having 1/3 as a value. So again, 1 divided by 3 times 1 to the 2/3 is 1. So this here actually provides me with a value that looks closer to 1 minus 3, which is actually a negative 2. So you'll notice that this actually bounces past the 0 that we know is there. Okay, so again, we tried 1 on a graph took us to a negative 2 somewhere way over here, not to this 0 point. So what we're going to do is we're going to go ahead and use negative 2 as my x1 value. So when I go ahead and do that, x2 is equal to x1 minus f of x1 divided by f prime of x1, again using this negative 2 value. Now we might worry because of this root function here, but keep in mind that this is a cube root in both of these cases, and a cube root will not have any negative issues. So when I plug in negative 2 to this, I'm going to get a negative 2 minus my f of negative 2 divided by f prime of negative 2. Now again, if you use all of your skills and your rules to evaluate these two functions at negative 2, and you try and simplify this function down, you'll actually end up with a value of approximately 4. So now you've gone from this value right here, which is x0, to this value over here, which is x1, and then bounced back past to x2, skipping over this number 0 that we know right here is what we're supposed to end up getting. So we get a value of 4, which doesn't actually work for us. Well, let's try and maybe this is bouncing around. It'll contain and bounce back to where it should be. Well, if I plug in 4 now, I'm going to have x3 equals to 4 minus f of 4 divided by f prime of 4. But if we evaluate these, again, plugging 4 into the original cube root function and plugging in 4 to this function here and simplifying that particular term down, 4 minus that number, we actually end up with a value of a negative 8. Which means, again, we've bounced further past 0 way over here. If we keep doing this, we'll end up with x to the 4th actually equaling to 16. And again, this thing continues to bounce out of control. The two reasons I did this example is, number one, so that you can understand that this notation right here can provide you with your f of x. If you get the equation equal to 0, then your f of x is actually what that thing is when it's equal to 0. The second reason I did this is because Newton's method is not always going to work. There are certain examples where your starting point will make everything off because of the way the tangent line approximation is going. Again, if you're not comfortable with this, you can arguably see it happen using the cube root function. There's my cube root function. If I pick 1, notice my tangent line again very clearly pounces past. Then if I pick 2, that negative 2 value, you'll notice again it bounces past way a heck over here. And if I again use that value right there, it's going to get even further out, and it'll just keep doing that uncontrollably. So using 1 as our starting point for this example actually doesn't work. We might have a better chance if we were to attempt to use, say, 1/2. That might actually allow us to bounce back into 0 as a bounce away from 0 as our approximating function.